Hello students, I've just recorded a bunch of videos from 9.5 and all of chapter 10 where I went through the workbook, but I just did the work and I didn't show you any Desmos graphs, which is unfortunate. So I'm going to go back through the workbook, you can see it here on the screen, and I'm going to just bring up some stuff in Desmos as we go. So this very first thing we did with 1 over x squared plus 1, I just want to show you what this looks like in Desmos. So here's the graph we're trying to model. And I'm going to show you, right off the bat, I'll show you a hint. So we could type it out like this. There's the first approximation. It gets better, and then it gets better. And you can see this stuff on the outside kind of going up and down. This is the stuff that's in your workbook. But if I wanted it to go farther, I can type SUM and make a sum in Desmos, which is very helpful. And we already figured out the pattern in the workbook, right? It was like this, but we want n to go from 0 to infinity, but Desmos can't do that. So I'm going to make a slider. I want this to be integers. So step of 1, and we'll go from 0 to, we'll do 100. And this will already break Desmos pretty hard. Desmos struggles with this, but you'll see what happens. And you can see how this is getting tighter and tighter. And remember, the radius of convergence for this was only -1 to 1, so there's not much is happening at this point. It's better. It's a little bit better than our blue one, right? But you can barely see the difference. And you can also see that at 1 and -1, it's never really going to get there, right? These were open endpoints for our radius of convergence. So they're always going to have these issues right at 1 and -1. And Desmos is kind of struggling to graph the stuff at the end, but you get the idea. So and then when they said we could integrate this, now I'm not sure how well Desmos would do this. We'll see. We'll do around there. Let's go to that one. When we integrate the red one, we should get arctangent. And so let's make it red and say we get rid of that old red one. And then, presumably, if we do the integral here, I don't know if Desmos will really do this. Well, we know how to do it. We can use the power rule. So this is really 2n, don't forget. We should really separate this -1 to the n, and then x to the 2n, and get rid of this thing. Like that, right? That's what we did, really. And you can see how that would model the original derivative of arctangent. So that's the green graph. Get rid of this guy for a minute. So the green and red are the same. And so now I want to model the arctangent function, and I'm going to integrate this. So let's copy this version. How do you integrate this? You increase the power by 1, and then you divide within here by the new power, right? That's what you do for integrals. And so now this new graph, we'll make it green to get rid of the old green, is modeling the arctangent function. Now the interval of convergence won't change. The endpoints might. In fact, we found out that the endpoints did, because I plug in 1, right, to estimate pi. And so now you can see that 1 and -1, this is actually looking pretty good, where we didn't have that before. But it still doesn't work past that, right? You can see these crazy asymptotes going outside of that. But it goes a little bit past, right? So 1 and -1 work and make sense, whereas that didn't happen for the previous graph. So when you integrate and differentiate, the endpoints can change, the radius will not. All right, so let's go back to the workbook. What was the next thing we talked about? We talked about these functions here, and I'll go ahead and just do one of these. So the very first one, I don't even know what this function is. It's not a Taylor series, like we talked about in chapter 10. But it's a function that has a domain, makes sense, and we found out to be -1 to 1 closed. So I just want to show you that any function you want, you can put here. So x to the n, and I think it was 2n squared. So we don't care about arctangent anymore. We don't really want to start at 1. We don't want to divide by 0. So let's start k equals 1, and then let's do this. And you can see that from -1 to 1, this graph makes sense, and outside of that, it's being kind of crazy, right? So we got the correct radius of convergence. And I don't know that this models a function that we know, but there are lots of functions out there that we don't give names to, right? Cosine x and sine x, negative x are all nice, but there's plenty of other functions out there. Any graph that passes the vertical line test is a function, right? Like an EKG graph or something. So we can use power series to model functions that we don't really know otherwise. and this would be one of them. Okay, so then we talked about integrating arctangent, integrating ln. I don't think you need to see this graph necessarily, but what I do want to show you is cosine, sine, and e to the x. So these graphs are different because their radius of convergence is infinite. So we eventually found out that cosine x's pattern was kind of this complicated thing we did in chapter 10. It's x to the 2n over 2n factorial, but it also had an alternation, and it started at 0. So let's add our k slider back. Let's give it a started at 0, go to 100, we'll give it a step of 1. And this should look like cosine x. So that's already the cosine x quadratic. And what happens when I do this out? So I'm actually going to play this. We'll zoom out a bit. It'll be kind of fast, but look how fast that already is just weaving out. That was too fast. It just becomes more and more of cosine. Now it's better near the center, right? It's centered at 0, and it just gets better and better and better. Right now, it's still not a good approximation for big numbers, but it will be if I keep going, except Desmos is going to start crying. So I'll stop, but you get the idea. It kind of expands out from there. Sine of x works the same way, but if you remember the sheet you had with the x's on it where we talked about doing e to the x at a different center, let's talk about e to the x and with a different center and with the regular center. So let's get rid of these for a minute. Let's look at e to the x, which is just x to the n over n factorial. And we also found a different version of e to the x centered at 2, and we had an e squared out front right here, but then we were also looking at x minus 2 to the n. Okay, so if I did this right, here's e to the x, here's the normal Taylor series that approximates e, and if you look at it at the beginning, it's really good around 0. It's not that good around 2 yet. See where 2 is? It's not a great approximation. But then it is, right? Once you get to about the 5th approximation, it's good. And it keeps going, and it keeps getting better everywhere, right? Okay, but you might really want to do really simple math because you're trying to solve equations or something, and you don't want 5 terms. You don't want a 5-degree polynomial. You want a 1-degree polynomial. This isn't very good at x equals 2. This guy is really good at x equals 2. And then you can see that they both become the same graph. And it looks like the green one is ahead of the purple, but really it's just on that side. If you go to the other side, they're just too big for you to see. 2 is to the right of 0, so the purple one's doing better on the right side. And way at the beginning, the purple graph, let me zoom in, the purple graph is doing way better around 2, not so good over here. The green one's doing better at 0. So it just depends on the application where you want to center your series at. If I only want a few terms, then I want this, even though it looks a little weirder. It'll be much easier to deal with a quadratic than having to go to like a quantic or something. So that's why we might center a Taylor series at a different place. All right, so going back to the workbook here, talked about cosine, talked about e to the x, talked about changing center like we did here. Talked a little bit about these. There was a couple of ones. Oh yeah, I wanted to show you guys, the last thing I wanted to show you guys was this crazy graph here where we got kind of a weird radical because we did the quadratic formula and all that stuff. So let me show you guys this situation. So originally we're not really thinking about Taylor series. In fact, we don't need these. The question is, where is 2x e to the x? So there's a graph. And x cubed plus 1/8. Where do these intersect? Okay. So we got, I said use one of the answers that we got, not both, but the answers we got were these. If I did all my math right, we got minus 2 plus square root of 5 all over 4. And I'm going to call this, if we call these f and g, if I plug this into either one, I should get about the same answer. So let's copy this and say that we plugged it into f. Okay, so here's the point where they intersect and presumably they agree. If I plug it into g, I would get about the same point, right? Because they're supposed to be equal, although this is an approximation. The other point we got was if you put a negative here and then you put a negative here, Notice that that is on the black line, but it's not really the point of intersection. It's off. So both were approximations, but the blue dot is much better. Why is that? Well, because I used a Taylor quadratic of e to the x centered near 0. So the closer my x values are to 0, the more accurate it is. So when I plug in that crazy point to the smaller number, I get a pretty good approximation of the point of intersection. When I put it over here, I don't get it in the right spot because it's farther away from 0, so the approximation is worse. I would have needed more terms to do something accurate. So that's something to be aware of. We're not going to go into the section on error, but the general idea that you should have is that, hey, the farther I am from my center of my approximation, the more I should think about using more terms or recentering my series. All right, I think those are all the graphs I wanted to show you guys, so I will stop there.